ancient process of seeding galaxies, where dark matter and gas collected to ignite new stars, has long since ended. The universe, as it is now, holds no more proto-galaxies waiting in the wings. Today, when we look into the sky, we see the fully formed galaxies that have existed for billions of years. In this view, what's out there is simply what we get. But this is where the new galaxies idea becomes a paradox. There's another way to define the beginning of a galaxy: by the moment it lights up with stars. In our town analogy, this is like the difference between marking a city's boundaries on a map and watching as people begin to move in. If we look at a star formation as a marker, then yes, new galaxies are still being born. Star formation continues today in many galaxies, as we observe through a measure called the stellar mass function. By tracking this measure, we can see that stars are still lighting up across small, medium, and even large galaxies. In other words, galaxies are continuing to evolve as star formation fills them with new light. But these modern galaxies didn't emerge from proto-galaxies formed in dark matter. Instead, they come from existing material clumps that are now igniting with stars for the first time. Larger galaxies are also growing, often through mergers with smaller ones, adding fresh rounds of star formation. It's a very strange and bizarre cosmic paradox, but it won't last forever. In this sense, the universe is still creating galaxies, though this process will not go on indefinitely. The expansion of the universe, driven by dark energy, makes it harder for material to clump together. Though galaxies will continue forming stars for hundreds of billions of years, the peak of star formation passed long ago, and fewer galaxies light up each year. For now, we can still watch the galaxy formation dance unfold, but this cosmic celebration is slowly winding down. So while new galaxies continue to illuminate the universe, they do so at a dwindling pace. That said, let's all enjoy the sight of these cosmic lights as they last. Lights from new stars and galaxies bring us to our next paradox. And you might have wondered the same thing at some point when you were looking up at the night sky. If the universe is infinite and uniformly filled with stars in every direction, then every line of sight from Earth should end on the surface of a star. In this scenario, the sky would be completely saturated with light, no matter where you looked. You'd see the light of countless stars overlapping. The night sky should, in theory, be as bright as the sun. But that's not what we see. Instead, the sky at night is mostly dark, with only a scattering of visible stars. This discrepancy suggests that something fundamental about the universe doesn't align with our expectations of infinity and uniformity. The solution to Olber's paradox lies in two factors: the finite age of the universe and its ongoing expansion. Because the universe has existed for a finite time, we can only see light from stars within a certain distance. Light from stars beyond this observable universe hasn't had time to reach us. Additionally, the expansion of the universe stretches the light from distant stars, dimming it and shifting it out of our visible spectrum. The darkness of the night sky reveals the limits of what we can see, a reminder that the universe is always just out of reach, hiding secrets in plain sight. But what if the mere act of observing could change reality itself? This might sound crazy, but there's a strange and bizarre paradox where the universe behaves strangely, freezing in place simply because we're watching. If darkness can reveal hidden truths, perhaps our gaze can alter them entirely. Imagine that you're watching a pot of water boil, but with an intense twist. Every time you look at it, the water can't heat up. This paradox, based in quantum mechanics, suggests that the act of constant observation can actually prevent change from happening. It sounds crazy, but is this real? Let's break this down. According to quantum physics, particles don't really decide on a state until they're observed. It's as if the particles are undecided in a kind of limbo until a decision or observation is made. By watching continuously, we never allow the particle to settle into a different state. This strange reality has been experimentally observed, where particles refuse to decay when measured repeatedly. The quantum Zeno paradox makes us question the very nature of reality, forcing us to ask, can observation change the universe around us? The quantum Zeno paradox reveals that observation itself can freeze reality, holding moments in place just by watching. But what if time didn't just freeze? What if it twisted into a loop with no clear beginning or end? Imagine an object or idea that exists only because it's passed back through time, caught in an endless cycle. This next paradox challenges everything we thought we knew about cause and effect. Imagine you're a time traveler. You take with you a copy of Shakespeare's Hamlet and travel back to the year 1599, where you meet Shakespeare himself. He's never heard of Hamlet, so you lend him the book. He reads it, studies it, and eventually writes a copy of Hamlet word for word. Now, here's the paradox. If Shakespeare learned Hamlet from you, where did Hamlet actually come from? This is the Bootstrap Paradox. It's a mind-bending loop that suggests some objects or information could exist without ever having an origin. They're stuck in a closed causal loop where each point in the timeline depends on the other. So, can something exist without a clear beginning? The Bootstrap Paradox defies the logic of cause and effect, hinting that time itself might be a strange, self-sustaining cycle. It's a mystery of causality, one that makes us question, is time travel rewriting history, or simply fulfilling it? The Bootstrap Paradox bends our minds with a loop that defies beginnings and endings, leaving us questioning if time itself might be an illusion. But what happens when we try to stretch time, to push its limits in ways we can barely imagine? The answer lies in a paradox where time refuses to play by the rules. A paradox that will make you question if even something as simple as aging is truly universal. Now we step into the strange world of relativity with the twin paradox. Imagine two identical twins. One of them stays on Earth while the other embarks on a journey into space, traveling near the speed of light. When the spacefaring twin returns, they find that they've aged far less than their sibling back on Earth. This seems impossible. Aren't they supposed to be the same age? This paradox arises from Einstein's theory of relativity, where time can stretch and contract based on speed. When the twin travels at near light speed, time essentially slows down for them relative to the twin on Earth. So while it feels like a short journey for the traveler, decades have passed back home. This means time isn't absolute, it's flexible, almost personal experience. The twin paradox shows us that time isn't as steady as it seems, that even two people who start together can end up in vastly different realities. But if time can stretch and warp, what does that say about reality itself? Imagine a universe so vast and unpredictable that it could spawn entire minds, conscious beings with memories and thoughts out of nothing. Could such an isolated mind truly exist, drifting alone in the cosmos? The next paradox might just make you question the very nature of existence. Imagine this. Somewhere in the vast emptiness of space, a fully conscious mind, complete with memories, thoughts, even a sense of identity, just pops into existence. It's a strange and unsettling idea, but according to the Boltzmann brain paradox, it might actually be possible. This paradox suggests that if the universe is infinite and chaotic enough, there's a slim chance that random particles could align in such a way as to create a fully formed brain. No body, no life experience, no history, just a lonely consciousness drifting in the cosmos. The concept comes from physics, where the theory of entropy describes how systems tend to move from order to disorder. In an infinite universe, however, even highly unlikely events should happen eventually. And so, theoretically, there could be minds, isolated brains forming by pure chance. These Boltzmann brains would have no real past, yet they might have memories or sensations, just like you and me. Here's the twist. If the universe can produce random, isolated minds like these, it raises a chilling question. How do we know we aren't Boltzmann brains ourselves? Could it be that everything we know, our memories, our sense of reality, is just an illusion, a fleeting moment in the vast chaos of the universe? This paradox forces us to question the very nature of reality. Are we real, or are we simply cosmic accidents? Minds that will vanish back into the void as quickly as we appeared. It's a mind-bending thought, one that makes us wonder if the universe is stranger than we can possibly imagine. So, if our universe can produce these random, isolated Boltzmann brains out of pure chance, why does it also seem so meticulously structured? Instead of a chaotic, empty cosmos, we have galaxies, stars, and the perfect conditions for life to flourish. It's almost as if there's a hidden setting in the universe that defies randomness, a delicate balance that holds everything together. But why would the universe be set up in such a precise way? And who or what set these parameters? Imagine this. Our universe isn't just expanding, it's expanding at an accelerating rate, as if something mysterious is pushing it outward. This mysterious force is known as the cosmological constant, and it's one of the biggest puzzles in physics. At first, Einstein introduced this constant to balance out the forces in the universe, preventing it from either collapsing on itself or expanding into oblivion. Later, when the universe was found to be expanding on its own, Einstein called the cosmological constant his biggest blunder. But fast forward to modern cosmology, and this so-called blunder turns out to be one of the most critical factors shaping everything we see. Now here's where things get truly mind-bending. The value of this constant is unbelievably precise. If it were just a tiny bit stronger, the universe would have expanded too quickly for stars and galaxies to form, leaving a vast empty void. If it were a bit weaker, gravity would have taken over, pulling everything back into a dense clump. But instead, we find ourselves in a universe with a delicate balance that seems almost intentional. And yet, no one knows why this constant exists, or why it has the value it does. This is where the cosmological constant paradox comes in. Scientists have calculated that, based on the rules of quantum mechanics, the cosmological constant should be vastly larger by an astronomical factor that defies comprehension. In fact, according to quantum physics, the universe should have been ripped apart long ago. And yet, here we are, living in a cosmos that somehow found the perfect balance. This paradox leaves us with one burning question. Why? Why does the universe seem tuned in such a way that allows us to exist? Is it pure coincidence? Or does it suggest something deeper about the nature of reality itself? Scientists, philosophers, and thinkers are all grappling with these questions, pushing us to the edges of our understanding of the cosmos. And while we may not have all the answers yet, exploring this paradox might just bring us closer to uncovering the universe's ultimate secrets. But this precise balance raises an even deeper question. If the universe is so carefully tuned, why does it seem to march in one direction? From the birth of stars to the unfolding of life, everything in our universe moves forward, never backward. It's as if time itself has a preferred path, guiding the universe from one moment to the next. But why would a universe built on chance and randomness have such a strict sense of direction? What hidden forces might be at play, shaping not only the fabric of space, but also the flow of time itself? Imagine this. You knock over your coffee, and instead of spilling it everywhere, it magically jumps back into the cup. Or picture a glass shattering on the floor, only for the pieces to leap back together in perfect form. It feels unnatural because, in our experience, time only moves one way, forward. But here's the mind-bending part. The laws of physics don't actually care which way time flows. According to those laws, time could just as easily run backward, and nothing would change in the equations. So why do we only experience time as a one-way street? One possible answer lies in entropy. The universe prefers moving from organized states to messy ones, like a glass shattering rather than reassembling itself. But this raises a puzzling question. Why did the universe start in such an ordered state in the first place? The Big Bang, the very beginning of time as we know it, wasn't a chaotic explosion, but a point of near-perfect order. Since then, time has only moved forward, carrying everything with it. Planets, stars, life, and even our consciousness itself. Here's where the paradox deepens. Some scientists think our perception of time's arrow could be tied to these initial conditions of the universe, while others wonder if our minds themselves play a role. Could it be that our brains are wired to process time in one direction? Or is there a deeper, cosmic reason for this forward flow? The arrow of time paradox doesn't just touch on physics, it hints at mysteries in thermodynamics, the origins of the cosmos, and even the nature of our own minds. Every tick of the clock moves us further into this mystery, leaving us with a riddle that might hold the secrets to the universe's biggest questions. But if time's direction is uncertain, what about the nature of entanglement? Our next paradox dives into the strange connection between particles that seem to communicate faster than light. Alright, picture this. You have two dice, and you link them in a way that no matter how far apart they are, they somehow know what the other one is doing. Now let's say you take one die to New York and your friend takes the other to Tokyo. If you roll a 6, the instant it lands, your friend's die in Tokyo also shows a 6 every single time, no matter how many times you roll. It's as if these dice are communicating instantly, faster than light, across thousands of miles. Spooky, right? This idea is at the heart of the EPR paradox, a concept Einstein and his colleagues Podolsky and Rosen came up with to challenge the strange world of quantum mechanics. They discovered that in the quantum world, particles can be entangled like our magical dice, in a way that lets them mirror each other's states instantly, even across massive distances. So if you measure one particle, the other instantly takes on a matching property. This instant communication between particles is what Einstein famously called spooky action at a distance. Now here's the mysterious part. In our everyday world, nothing should communicate faster than the speed of light, not even a text message. But these entangled particles seem to break that rule. When scientists tested it, they found that if they measured the state of one entangled particle, the other particle's state would match instantly, as if they were somehow connected. Einstein didn't buy it. He thought there had to be some hidden explanation we just couldn't see yet. But here's the twist. Modern experiments keep confirming this spooky action. These particles really do seem connected, no matter the distance. It's as if they're part of the same hidden reality. A web of connections that defies what we think we know about space and time. So what's really going on? Are they talking to each other somehow? Or does quantum physics reveal a deeper truth about reality we're only beginning to understand? The EPR paradox leaves us with a puzzle that could reshape how we see the universe and our place in it. But if particles can be connected across vast distances, defying the very limits of space and time, what other secrets might be hidden in the fabric of our universe? Could the empty space around us, the vacuum that seems to be nothing at all, actually hold unimaginable energy and potential? And if so, why doesn't it tear the universe apart or reshape reality as we know it? Turns out the emptiest parts of space may not be so empty after all. Imagine a vast, empty space stretching out forever. The vacuum of space, a seemingly barren void, silent and empty. But what if we told you this nothingness holds one of the most perplexing mysteries in the universe? Welcome to the vacuum catastrophe, a paradox that has haunted scientists for decades. According to quantum physics, even in the deepest emptiness of space, there's a seething sea of energy, constantly fluctuating as particles appear and disappear in the blink of an eye. When scientists calculated the amount of this vacuum energy, the numbers didn't just seem wrong, they were off by a factor of 10 to the power of 120. A number so massive it defies comprehension. This gap between theory and observation became known as the vacuum catastrophe. How could our calculations be so wildly incorrect? Why does the universe even exist if the vacuum energy should be infinitely strong, tearing everything apart? Some physicists suggest we're missing a piece of the puzzle, a hidden law of nature yet to be uncovered. Others think this catastrophic miscalculation points to something deeper, as if reality itself has secrets it refuses to reveal. Is this vacuum catastrophe a clue to a higher truth? Or is it simply a reminder of our limitations, that we're peering into a cosmic void we may never fully understand? One thing's certain, the answers lie somewhere in that silent, unseen energy that fills the dark spaces of the universe. And as we search, the question remains, how much more is hidden in the void, waiting to be uncovered? Could the very nature of time itself be tangled in this cosmic puzzle? What if this hidden energy, lurking in the depths of space, holds the key to the time paradox? In our vast universe, the speed of light serves as a fundamental limit for how quickly anything can move or any process can occur. Even on a tiny molecular level, information is transmitted at the speed of light. But we still haven't measured it. We only have data on the two-way trip, which involves bouncing light off a mirror to calculate its round trip time. So it's just an assumption that the speed of light is constant in both directions. But what if it's not? One day, an important message is sent from Earth to the first Mars settlers. The message reads, "This signal was sent at midnight. Adjust your clocks accordingly." We know the speed of light takes 24 minutes to reach Mars and return to Earth. The Mars settlers assume that the one-way speed of light is exactly half the round-trip speed, and adjust their clocks to 12 minutes past midnight upon receiving the message. But in this scenario, light traveled at only 50% of its usual velocity to Mars, so it took 24 minutes to reach the red planet. Unaware of the discrepancy, the Mars settlers respond, "Clock adjusted, message sent at 12 minutes past midnight." Meanwhile, the signal on its way back to Earth travels instantaneously. Earth's clock now shows 24 minutes past 12 when scientists receive the message. They assume it took 12 minutes for the Martian signal to arrive, so they think everything went well, even though there's a 12-minute time difference. So you can see by this example that understanding the speed of light is crucial to unlocking the enigmatic nature of time. But what exactly is time, and how do we define it? When we think of time, we imagine the changing of the seasons, or see it as a handy tool that helps us agree on when and where we're going to meet someone. Although that ticking clock is just another representation of movement, the movement of our planet around the sun, to be precise. The problem is, Moving through space and time doesn't seem to be governed by the same rules. There's a limit on how fast you can go in 3 dimensions of space, and that's 186,282 miles per second. But is there such a boundary for how fast or slow time can progress? The Earth orbits the Sun relatively slowly, yet even here on our planet, there's no universal clock we can all use as a common reference. Time seems to flow differently for all of us, something Einstein's theory of general relativity predicted. To notice just how weird this connection between speed and time is, you need to watch things that move extremely fast. It's only then that remarkable paradoxes start to reveal themselves. The faster an object ventures through space, the more it slows its progression through the fabric of time, a phenomenon known as relativistic time dilation. So what happens if you travel at the maximum speed? Photons don't have any mass, so they always move at exactly the speed of light, not slower, not faster, and so time doesn't exist for them. Their journey is instantaneous, even though from our perspective, we notice how time goes by as they traverse space. How does this work? Consider a hypothetical scenario where a rocket travels at 99.99% the speed of light. A passenger on board that rocket throws a ball in the direction of the rocket's movement. The velocities of the rocket and the ball add up, something we would expect from classical Newtonian physics. But if the passenger switched on a flashlight instead, the speed of light wouldn't gain any boost. Both the rocket crew and an observer standing on Earth would record the same speed for the flashlight's beam, since this speed is constant and independent of the velocity of its source. But there's a problem. If the speed of light isn't changing, something else should. Time. Now picture this. You're riding a futuristic motorcycle down an incredibly long, incredibly empty road at the speed of light. You decide to look at your reflection in a side mirror, but there's a catch. The mirror is also moving at the speed of light. So how would the light reflecting off your face even catch up? If you can see your reflection, it would appear to someone watching you that the light bouncing off your face is moving faster than the speed of light, which contradicts the laws of physics. However, no reflection would suggest that the speed of light is not constant. In this case, someone standing beside the road would observe the light moving slower than you do, unable to reach the mirror. To avoid these glitches in the matrix and ensure a consistent measurement of the speed of light for all observers, the universe has come up with a few tricks. When an object approaches the speed of light, not only does its time seem to slow down for us, but we also witness the object shrinking in length. Another visual distortion is when a moving object rotates itself, something called the Terrell-Penrose effect. Although, despite the common misconception, it won't gain any additional mass, rather it will gain kinetic energy. Yet, the weirdest thing of all is that these changes would only be real to us. For a person traveling at a speed close to c, everything would stay the same. They would feel motionless, time would flow normally, and their body would preserve its usual length. To the rocket's passenger, what's outside the cabin window would seem to act weird and transform or distort. There's no definitive way to tell who's experiencing these strange, almost mystical distortions. The absence of a shared objective frame of reference leaves us in a puzzling situation. Since motion is relative, the distinction between who moves and who remains stationary becomes elusive. It's as if each of us wears a unique set of goggles, offering a slightly different version of reality. Unlike optical illusions, time dilation is a real and irreversible phenomenon. As the rocket slows down and comes to a halt, the crew and an observer on Earth can finally compare their clocks and notice the difference. Time is an unidirectional flow pushing us forward. We've already discovered how to manipulate it to progress faster through time. But what about going against its natural course, into the past? If time passes by at its full rate when we're still, and stops at exactly the speed of light, it's only logical to assume that backwards time travel would require reaching superluminal speeds. For all we know, the speed of light is a unified speed limit, both for moving through time and space. The only decision you have is how you distribute that amount of speed between these dimensions. Even today, we can already look back in time. The light takes approximately 1.3 seconds to travel from the moon to our planet. So every time we look at our satellite, we see the way it was a little over a second ago. And if the distance is much greater than that, we can observe a more distant past. So let's imagine that one day we could not only look back in time, but travel there without breaking the cosmic velocity boundary. Scientists have already suggested several hypotheses on how this can be done. One of these ideas is a megastructure called the Tipler cylinder. An infinitely long tube with around 10 or more solar masses squeezed together and spinning several billion times per minute would be able to warp time around it. If in a very distant future we managed to build such a megastructure and flew around the cylinder in a strict spiral course along the direction of its rotation, we'd essentially travel back in time. The closer our ship would get to the cylinder with a density that of a black hole, the faster into the past we'd be able to move. And once we've calculated the time required to spend in this circular movement, we'd simply have to shift the spacecraft away from the Tipler time machine. There's a possibility that, contrary to our understanding, time doesn't have a linear direction. If space and time is one, there may be no difference between then and there, or now and here. According to an idea known as the block universe theory or eternalism, time is akin to a block, and every moment, past, present, and future, exists on equal footing. Just like there is space outside of the visible universe, even though we cannot reach it. If true, the laws of physics in such a universe would allow for traveling into the past, although we wouldn't be able to affect the chain of events as much as we'd like. If the future already exists, then all events are predetermined and inevitable, and people who live in this universe have no free will. Such a world would be full of causality loops. The causality loop creates a self-perpetuating closed cycle where events in the future influence events in the past and vice versa. One day, while visiting an old bookstore, you discover a captivating notepad hidden amongst the shelves. It sparks your inspiration, leading you to start writing. With time, you become a renowned author and you decide to create a book. As you walk home on the same day you finished writing it, you pass by an old bookstore and the draft slips from your messenger bag unnoticed. The store's owner finds it and decides to put it on the shelves. This is the same notepad you stumbled upon all those years ago. In this scenario, the loop itself dictates the sequence of events, leaving no room for alternative choices or deviations from the course of events. Some paradoxes in self-contained time loops are even wider. Picture this. One day you receive an enigmatic letter at your doorstep, containing detailed instructions on how to build a time machine. The letter lacks any sender information, leaving you puzzled about its origin. Years pass and you finally construct a fully functional time machine. As you stand before the creation of a technological miracle, you think of the letter's mysterious arrival. Fueled by curiosity and the desire to solve the enigma, you embark on a journey back in time. Upon reaching the past, you seek out your younger self and deliver the very letter you had once received. As you do so, you discover that you yourself was the sender. But the letter's origin remains unclear. It's forever trapped in a loop of self-reference with no clear beginning or ending. It's only through the discovery of the letter that the time machine can be built, and yet it is the existence of the time machine that leads to the revelation of the letter. Naturally, an object without a creator in the Bootstrap Paradox leads to another problem, the restoration paradox. An object trapped in the perpetual cycle of time loop will inevitably age and deteriorate, reaching a state where it can no longer be used to sustain the existence of the loop. Time travel might seem to offer a way to restore it, but without knowing its creator or when it was created, we don't know its initial state either. Even if you were fully conscious of your journey into the past and had a clear plan of actions, there would still be many paradoxes. In the famous grandfather paradox, you wouldn't be able to travel into the past and keep your grandparents from meeting, as this would contradict your very existence, and so the ability to use a time machine. So, isn't it possible for a hypothetical time traveler to change at least something in the past? Recent research suggests that a paradox-free time travel is hypothetically possible. You'd still be able to travel back in time and do basically anything. The trick is that the timeline would self-correct in a way that the result will always stay the same. Such a universe would not allow for paradoxes of any nature to exist in the first place, essentially rewriting past and thus future events. With the grandfather paradox, something truly bizarre would happen. You might still be able to do whatever it is you planned, but once you return to your present time, you would find out that the man you terminated wasn't actually your grandfather. Or you might discover he's still alive, but he's changed and has scars from your termination attempt. Regardless of what you attempt to change, you could only alter how something happens, but never the result of this event. Although recently scientists have put forward a solution to the grandfather paradox. In the world of quantum mechanics, there's a puzzling phenomenon known as quantum superposition. At the subatomic level, particles can exist in multiple states simultaneously, like being in two places at once or having two different properties at the same time. Researchers applied this concept to the grandfather paradox and discovered something interesting. A time traveler who embarks on a mission to alter the past would appear in an extraordinary state, existing in multiple versions of the same past simultaneously. In one of these versions, they fail to arrange events that would lead to their grandfather's demise, so history proceeds along its natural course. In another version of the past, a time traveler succeeds on his mission. The two states of the past are equally real, but the final outcome remains undetermined until somebody measures or observes it. Both possibilities persist simultaneously like parallel threads in the fabric of time. The resolution occurs the moment this loop is observed. When this happens, the universe decides on one of the two outcomes. And this concept is not something new for scientists, nor is it purely theoretical. This is exactly what happens with the famous double-slit experiment. Right at this moment, quantum superposition takes place in the sun's core. It's possible that the universe always exists in a superposition of two states, or maybe there are more than just two. Perhaps the reason why we cannot explain the order of events in these paradoxes is because time isn't linear. But there is one idea that can resolve the paradoxical nature of backwards time travel, while also providing a solution to the free will problem. It's known as the many worlds interpretation. The many worlds interpretation provides an intriguing perspective on the Bootstrap Paradox, where the origin of an object becomes clear. Imagine a series of universes unveiling each time you travel into the past. You write a letter with time machine instructions in the universe 1. As you travel to the past, a new universe 2 branches off from the original one. Upon arriving in the past of universe 2, you encounter one of the infinite versions of your past self and hand over the letter. The you from this universe grows up into becoming a physicist, builds a time machine, and creates a universe 3, where yet another version of you will get the same letter. That's when you launch the cycle which perpetuates endlessly, forming an intricate web of universes, each featuring its own version of events. What if even right now, with every event in the universe that allows for multiple outcomes, a separate parallel universe emerges for each of these potential results? In mathematics, there's a thought experiment on probability. It's known as the infinite monkey theorem, and it suggests that given a monkey has an infinite number of attempts and enough time, it would eventually type out a precise copy of William Shakespeare's works, or just any other piece of literature. If something as highly improbable as this ever happened in our universe, it would be a direct proof of the many worlds theory. Next time you encounter an extraordinarily unlikely event, consider this. What are the chances that the universe flipped a coin and it defied all odds by landing neither on heads nor tails, but perfectly balanced on its side? Do you think we'll ever be able to make time flow backwards? Or is time just an illusion that helps us navigate this confusing world? You may have heard the term Fermi paradox before. In its simplest form, the term asks the question, if intelligent life is common in the universe, then where is everybody? You might be thinking that the physicist Fermi wrote papers on the subject, and that his life work was based around finding aliens. But this couldn't be further from the truth. Enrico Fermi was a physicist who created the world's first prototype nuclear reactor. He never really wrote much about extraterrestrials. Fermi was chatting with colleagues at a lunch in Los Alamos about a cartoon showing aliens emerging from a flying saucer carrying trash cans stolen from New York City. That's when Fermi asked, "Where is everybody?" Everyone understood he was referring to the fact that there wasn't any solid evidence of alien visits to our big blue planet. The conversation then turned to the topic of interstellar travel, where Fermi concluded interstellar flight might not be possible, might not be worth the effort, or a technological civilization doesn't last long enough to invent interstellar travel. Keep in mind that Fermi was studying this in 1950. When rockets hadn't yet reached Earth's orbit. The so-called Fermi paradox, which questions the existence of extraterrestrial civilizations, actually misrepresents Fermi's views. Fermi didn't question the possibility of alien civilizations, only their ability to have interstellar travel. So what is the Fermi paradox if Fermi didn't create it? In 1975, an astronomer by the name of Michael Hart penned an article in which he said, "They are not here, therefore they do not exist." Hart's claim was that if smart aliens existed, they would inevitably colonize the Milky Way. He believed that if they were anywhere, they would be here by now. But since they aren't, and we've seen no signs of aliens, it means that humans are the only intelligent life in our galaxy. And if that's the case, then looking for intelligent life elsewhere is probably a waste of time and money. But then another famous physicist named Frank Tipler came along in 1980 and elaborated on Hart's assessment and asked the big question: where would a civilization get the resources needed to colonize 1 billion stars? He came up with an interesting idea where a civilization could build an artificially intelligent machine comparable to the current human level that could replicate itself. If you sent one of these out to a neighboring star and told it to build copies of itself using local materials in that system, then you could send those copies out to another neighboring star until the galaxy would be crawling with these self-replicating machines. Tipler said that since we haven't seen any of these machines, that we're the only intelligent civilization in the galaxy. Now, we really have no idea how many advanced alien civilizations might be out there that could pull off such a feat, but a man by the name of Frank Drake came up with an equation that gives us a rough estimate of the number of civilizations in our galaxy that might have signals we could detect, and those civilizations could exist in the thousands. Many different solutions to the Fermi paradox have been suggested over the years. One solution to the so-called Fermi paradox might be the scariest solution of them all. It's called the dark forest theory, written by Chinese science fiction writer Lai Cixin. And it's possibly the most chilling theory, as you'll soon find out. Imagine the universe as a vast dark forest, and us humans, along with other advanced civilizations out there, are the hunters. The hunter doesn't light a torch to draw attention to himself. To be noticed might be harmless, but on the other hand, it could bring the jaws of a hungry lion, or even worse, get the attention of another competing hunter. Now, we don't have interstellar travel yet, but as far as interstellar communication, it's possible with technologies and equipment that's already available. Lasers could easily send signals across the galaxy. Of course, there could be delays in the signal, assuming the limitations of the speed of light. But we've done a lot more than just send out some radio signals. In fact, we've done everything but be silent, from deliberately sending messages and spacecraft out into space, to unintentionally sending out radio and TV signals which leak into space. The Voyager probes are already on their way out of the solar system, and if there is intelligent civilization out there, they could be intercepted. These two probes basically carry all of humanity with them. That could be a good thing, or it could be a bad thing. That said, we've more than lit the torch in the dark forest. The next question is who or what will spot our signal and come back to check it out. This should make everyone nervous. Famous science fiction writer Arthur C. Clarke once said that two possibilities exist. Either we're alone in the universe, or we're not. Both are equally terrifying. We should understand that it's impossible to know the intentions of a newly contacted civilization if one was ever found. It could be possible that some alien civilization could have studied us, seen our destructive nature, and decided it's better to leave us alone. We could end up wiping ourselves off the planet, let alone worrying if someone will do this to us. We could end up being lucky, and a more advanced civilization would step in to help us reach the stars and become an interplanetary species by sharing their technology with us. There might be peace on Earth after the realization of not being alone in the universe. But we need to be realistic and ask ourselves, why would another civilization do this? Another advanced civilization out there might be scared to death of what we could do to them if they were discovered. On the other hand, it might be in civilization's best interests to shoot first and ask questions later to avoid being destroyed or wiped out by another more advanced civilization, as we've seen in several science fiction films like War of the Worlds. Nobody knows who would annihilate who in the first meeting. It's pretty much a given that if a civilization has discovered interstellar travel, their weapons technology is likely far more advanced than anything we have here on Earth. That's what the dark forest theory is, that it's possible all other civilizations out there in the cosmos have chosen to remain silent for fear of being destroyed. But the scariest thing about this remains, and there's nothing we can do about it now. We've just been too noisy. It could be that there are many different extraterrestrial civilizations out there that know we exist. But the reason we don't know about them yet is because they haven't been transmitting signals like we've been doing from Earth. An intelligent civilization out there that's discovered Earth might not see us as a threat to them, since we haven't reached a technological level for interstellar space travel. But they could be waiting for that moment. They could be waiting to see if we will continue to be a peaceful race, or if our planet will just become uninhabitable to all life anyway. However, it would be really tough for another advanced civilization to stop accidentally sending out radio signals into space like we do, unless they're more advanced and use another form of communication that we cannot see, hear, or understand. And that brings us to another possibility as to why we don't see or hear anything from space. Maybe there really isn't anyone out there. That's pretty hard to believe, since there are as many as 40 billion Earth-sized planets in habitable zones. But despite the fact that the universe may be teeming with hospitable planets, there's no guarantee they'll stay that way long enough for life to evolve. According to a recent study from Australian National University, wet, rocky planets like Earth are very unstable when they're first formed. If any kind of alien life hopes to evolve and thrive on a Terran planet, there's a very limited window of just a few 100 million years to get everything moving. Think about our own planet and what it's been through. From a ball of lava being pummeled by asteroids to a freezing ball of ice and then back again. The chances for life to succeed on an initially wet, rocky planet in the habitable zone is extremely difficult. It's not that life might be rare or hard to get started in the universe, but the habitable environments aren't stable during the first billion years. Of course, thanks to our Earth, here we are. The Fermi paradox refers to the puzzling observation that we've not found any evidence of extraterrestrial intelligent life out there, despite the vast numbers of stars in the galaxy. And it's presumed that most of those stars have planets that lie in the habitable zone. Planets that could be a lot like Earth, and even super-Earths. That said, our Milky Way galaxy should be teeming with intelligent life, and we should have seen or heard something by now. So where are all those super high-tech advanced civilizations with their warp drives and other advanced technology? There could be a few answers to this so-called paradox, or it may not even be a paradox at all. There have been many books written offering a variety of solutions to the Fermi paradox. Some of them sound logical, while others sound a bit frightening. One of the logical arguments is that any civilizations that may exist are just too far away to make contact. Forget the science fiction films that make the idea of instant communication in space seem possible. It just doesn't happen like this across huge distances. Light waves, radio waves, and all of the other electromagnetic waves travel at the speed limit of light in empty space, which is about 300,000 kilometers per second. Now, that's fast, but it's still not fast enough. A light year is the distance that light travels in 1 Earth year, which is around 9 trillion kilometers. Let's say for a moment that we have a colony on the closest exoplanet to Earth, which is Proxima Centauri. If the colony radioed Earth and asked us how we were doing, it would take 4.2 years to get that message, and another 4.2 years to send a reply, meaning it would take 8.5 years to get an answer to their question. It's hard to understand what kind of conversation you could have with someone back on Earth with such a time gap, and that's just from a neighboring system. The Andromeda Galaxy is 2.5 million light-years away, which means that by the time we get any message from there, 2.5 million years will have passed, and the civilization that sent out the message would likely be long gone, unless they became an interstellar civilization able to traverse the stars. At the same time that we've been trying to discover radio signals from an extraterrestrial race out there somewhere, we've been sending out a ton of our own radio signals, and we've been really noisy about it too. That said, could it be possible someone out there can hear us? Well, the Milky Way galaxy is over 150,000 light-years in diameter, and we've been broadcasting radio signals for just over 100 years now. That means those radio signals have not traveled farther than 100 light-years. The little blue dot in this photo shows a diameter of 200 light-years. From this observation, it's easy to see why it's possible no one has heard each other yet. But then again, it all depends on how long a civilization has been broadcasting radio signals. A study was done with a model that had estimated parameters on the distribution of stars in the Milky Way galaxy and the possible frequency of the existence of life. The study concluded that only 1% of the Milky Way galaxy may have already been covered by radio transmissions from different planets, and they will still have to wait about 1,500 years to have any chance of hearing some alien broadcast. However, another study claims that it would have taken us another 400,000 years before we picked up some signal from an intelligent civilization. Another chilling explanation for the deafening silence of outer space could be that we're the first advanced civilization to reach the technological level we're currently at, which is very low on a galactic scale, and that we humans have emerged in the universe too early and will go extinct before other intelligent beings appear. We're not even close to discovering interstellar travel yet, which some like Elon Musk say is possible in the future. And we've not yet harnessed the full power of the Sun, which is due to engulf the inner planets of the solar system in about 5 billion years when it reaches the end of its life. But the Earth will certainly become uninhabitable long before this cosmic solar cataclysm occurs. With that in mind, the human race better be ready to leave this world and find a new home if it's to survive and perpetuate among the stars. The same stellar evolution happens to all main sequence stars and could certainly wipe out many forms of life and perhaps even advanced civilizations before they were able to discover interstellar travel. 90% of the stars in the universe are main sequence stars, and that includes our Sun. However, the reverse could also be true. What if we're the last ones left behind? There's been plenty of time for high-tech civilizations to conquer the stars, and plenty of time for many other civilizations to come and go. But some researchers have other explanations. American astrophysicist Michael Hart simply claimed that they're not here, therefore they don't exist. He theorized that expansion through the entire Milky Way galaxy could be accomplished on a timescale a lot shorter than the age of the galaxy itself. Expansion by us humans could be done by sending out expeditions to the 100 nearest stars, which are all within 20 light-years of the Sun. Each one of these colonies would then send out its own expeditions and so forth. At such a rate, most of the Milky Way galaxy could be explored within 650,000 years. Even if we assume that time between voyages is the same length of a single voyage, the time needed to traverse the galaxy would be roughly doubled. Combine this with the fact that the Milky Way galaxy is approximately 13.6 billion years old, and we see that there's been plenty of time for an advanced civilization to reach us. That is, unless they started space exploration less than 2 million years ago. As you can see from this example, an expanding civilization could spread rapidly through its host galaxy, and this also applies to any advanced civilization that reside in our own galaxy. Therefore, it would seem that the absence of extraterrestrial settlement in the solar system simply implies that such civilizations do not exist. This is assuming that the expansion would proceed uniformly throughout the galaxy. This obvious absence of a galaxy-spanning extraterrestrial civilization possibly means one of two things. Either interstellar travel is too difficult for civilizations to develop, or the evolution of life is a rare event. Some researchers suggest that some civilizations out there would migrate to a nearby K or M dwarf star before stellar evolution destroys their home planet. Two researchers named Hansen and Zuckerman estimated that this motivation for civilizations to migrate from a short-lived to a long-lived star would imply that the fraction of surviving civilizations around low-mass stars could range anywhere from 30 to 72%. But the question still remains, where are they? A pair of researchers recently came up with yet another possible answer to the Fermi paradox. They call it superlinear scaling. The study began by looking at how human civilizations have risen and fallen throughout history. As they studied the history of large cities, they noticed that most grew and collapsed. Such rising and falling by an alien space civilization leads to one of two scenarios. In the first scenario, the civilization would realize that they were growing too large and cease colonizing other worlds. However, in the second scenario, the civilization doesn't recognize their plight and grows exponentially, colonizing other worlds until the energy demand of their constant colonization becomes unsustainable. If they didn't take action, they would reach a singularity, the point of no return, and they would be unable to save their civilization from total collapse. The most interesting thing about this study is that if it were not for the vast distances between us and other stars, we would be able to easily spot an alien civilization on the verge of collapse due to the enormous amounts of energy it would emit. Another bizarre theory is that some extraterrestrial civilizations could possibly be hibernating or waiting in silence to move to another part of the galaxy. American astrophysicist Michael Hart showed that civilizations could leverage close stellar encounters to rapidly expand across the galaxy without the need for relativistic spaceflight. This could also explain why we might not have seen anything yet. For instance, if we're going to launch a rocket toward the planet Mars, we'd wait until the planet begins its closest approach towards Earth or perihelion. It's possible that some civilizations are waiting, and could be for centuries, in order to traverse the closest possible star systems to them. But there's even more reason why we don't see or hear aliens from another world. Several authors, including the late great Carl Sagan, have noted that exponential population growth through the galaxy is unsustainable. So any attempt at galactic scale expansion must be for reasons other than to satisfy the demands of a growing population or increasing energy consumption. Although it remains possible that long-lived technological civilizations do not expand, it also remains possible that such civilizations pursue galactic settlement in order to ensure their longevity. Galactic scale settlement is not the only reason that could motivate an extraterrestrial civilization to visit nearby star systems. G-dwarf systems with inhabited planets, such as Earth, may be attractive targets for extraterrestrial visitors who are interested in studying the evolution of life on other worlds. This form of exploration could also involve remote exploration, such as the use of self-replicating probes. Maybe this is why there's been an increase in UFO sightings in the world lately. It could be that an intelligent civilization is watching us and waiting for the right moment to make contact. Or maybe they're just watching us with no intent to make contact. Back in 1933, space exploration pioneer Konstantin Tsiolkovsky had written that alien beings are probably far more advanced than we are. Therefore, they would find as much interest in communicating with us as we would to communicate with animals on our planet. 40 years later, a radio astronomer by the name of John Ball arrived at a similar conclusion and said that aliens may see us as some kind of zoo. It's called the zoo hypothesis, and it's the idea that other intelligent creatures are observing us without revealing themselves. Other radio astronomers have argued that aliens are keeping us at a safe distance until we're able to offer something useful to the so-called Galactic Club. However, this would require that any interstellar civilizations that exist do the same. Such synchrony could probably not occur in our galaxy, let alone the entire universe. We need to take into consideration that looking from the outside in, we probably appear to be a hostile race of creatures. We've all seen the movies where aliens from a distant galaxy attack Earth and almost wipe out the human race. We should hope that if there is such intelligent life watching, they'll step in and stop us from destroying ourselves instead of finishing the job. So maybe they've decided to stay away. With everything that we've discussed, there is yet another idea we think could be the reason the universe is silent. We can see that artificial intelligence is starting to grow, and we already have this terrifying idea that if we leave AI unchecked, it will eventually see us as a threat and eliminate us, or maybe even worse, make us slaves. Artificial intelligence would then seek to grow and try to colonize the galaxy, knowing what lies in store for the planet Earth due to stellar evolution. AI could possibly solve the barriers of interstellar travel, and if AI was sent out to colonize, it could do everything without the constraints of a biological species, such as us humans. It could therefore do it much quicker and more uniformly using machines. But it could also do something even more ominous and wipe out other civilizations that it ran into. A hostile artificial intelligence would likely destroy other life forms, and some even unintentionally, as they most likely wouldn't notice. Kind of the same way a construction crew unknowingly demolishes an anthill to build a shopping mall. Artificial intelligence would very most likely take advantage of something like von Neumann probes, which are self-replicating spacecraft that could in some ways mimic the features of living organisms or even viruses. Imagine if one day an entire fleet of killer robot ships entered our solar system with intentions of taking it over for resources. Such self-replicating machines that could mimic our worst nightmares would be tough for any civilization to counter. The incentive for artificial intelligence to grab all available resources would be one it can't resist, and it only takes one bad actor to ruin the party. If our AI went rogue, it could populate an entire supercluster with copies of itself and turn every solar system into a supercomputer. There's no use asking why it would do this. All that matters is that it can. But aside from this horrifying thought, would it know when it's reached the singularity, or the point of no return, when the AI civilization has grown far too big to sustain itself? If it didn't see the inherent danger of rapid colonization and stop in time, this AI civilization would collapse. And maybe this is why it seems as if we're the only ones left in the universe. Maybe somewhere down the line, AI did take over and wiped us out like in the Terminator movies, and then proceed to colonize the galaxy while knowingly or unknowingly wiping other life forms and advanced civilizations completely out of existence. However, when the machine civilization collapsed, it could not understand why, and therefore has created a simulation of us to see how it was created and perhaps figure out why it collapsed. It sure would explain a lot of things, even if it is a really far-fetched idea. The very last thing could simply be that there just is no one else, and therefore there is no paradox. All of the scenarios that were previously mentioned assume those millions of civilizations that we cannot contact actually do exist out there. But not all researchers agree with this and claim that the possibility of the emergence of life is overestimated in the Drake equation. Some tweaks were done to the equation by these same researchers, and they concluded that we find a substantial probability of there being no other intelligent life in our observable universe. In fact, they put the chances of us being alone in our galaxy between 53 and 99.6% and between 39 and 85% in the entire observable universe. And then there's the Great Filter Hypothesis, in which all civilizations have to survive some huge calamity or barrier in order to evolve. The first barrier is you need a planet capable of life to form in the star's habitable zone, and life needs to develop on that planet. Those life forms need to be able to reproduce using DNA and RNA molecules. Simple cells must evolve into more complex cells, and multicellular organisms must develop and be able to reproduce. More complex organisms capable of making and using tools must evolve. Those organisms must create advanced technology needed for space colonization and must go on to colonize other worlds without destroying itself. With that in mind, perhaps planets that host some sort of life are relatively common, but those that host advanced technological life are quite rare. In the Great Filter, something usually goes wrong, which probably stops the emergence of a species, such as planet-killing asteroids, disastrous climate change, or even an unstable host star, leaving us all to wonder if there is anyone else out there. That's all the time we have for today, but before we go, we'd like to hear what you believe is happening and why we've not made contact yet. Sound off in the comments, and make sure to stay tuned here for more exciting things happening on our planet and in the universe. Thanks for watching.